Hello students, this video is going to be looking at radian measure. The idea that we're not always going to be using degrees as our angle measurement. We will sometimes use a different measurement that involves the value pi, and that is called radian measure. First, we'll talk about what the definition of a radian is. A radian is a measurement that has to do with the length of this arc on the outside of the circle matching the radius of that particular circle. Now, we've sort of been alluding in class to the fact that we're working towards this idea of what we call a unit circle, where the radius of this circle is going to have length 1. And so if we look back at this original picture, we think of the radius of the circle as being 1, we can think about this measurement of being length of 1 radian. Now, another idea to think about, because some of you sort of remember this from some of your classes you had in high school, is that when I go from the position of 0 degrees all the way to 180 degrees, this will have the measurement in radians of pi. And we know that pi has a decimal approximation of 3.14. So if we were to take this picture here and take this length of 1 radian, and then extend that same length, let's say, to here, which would be 2 radians. That's another r, so that total distance is 2. And then do that one more time. Let's say we go to here. Just before we get back to the x-axis, that will be our 3rd radian. And that is kind of lining up with what we know here, that we'll get to 3 radians just a little bit before we get to the x-axis again. If we were to go all the way around the circle, we would end up at a radian measurement of 2 pi. 6 radians, 2 pi is going to be about 6.28, just taking this number 3.14 and doubling it. And so 6 radians is going to be probably about here, just before we get back around to the x-axis again. Because we use the radian measurements more commonly in pre-calculus and calculus, we have to know how to convert between degrees and radians. And we use this proportion here, this fraction, to change between radians and degrees. Now, one thing to take note of is that technically I think that there should be a little degrees symbol here. We'll talk about that in a minute. I've got 2 fractions written in the reverse order, and sometimes students want to memorize which one to use in which context. You'll see in the future examples we have in just a minute that you don't need to think about that if you think about unit conversion and you think about what the units are that need to cancel. And so that helps you figure out which direction to have that fraction set up when you're converting back and forth. So in this first example, we're going to convert degrees into radian measurements. Radian measurement will oftentimes have pi symbols in them, like these first 2 examples do. But they don't have to. They can be a decimal number like that. And I'll talk about that in a second. For example A, we're converting 45 degrees into radians. And so the way that I would write this is I would leave this as 45 degrees and then write it as a fraction, 45 degrees over 1. And then you can see that if I put the 180 degrees down in the bottom, degrees and degrees are going to cancel each other out. What we're really ending up with mathematically is 45 times pi over 180. And if you put 45 over 180 into your calculator, that'll give you 1/4. And that's how we're ending up with this answer of pi over 4 radian. Following that same idea for the next example, if we have 270 degrees and we multiply that by pi over 180 degrees, I know that I want the degrees to be in the denominator of the fraction because they're in the degrees are in the top of the fraction that I'm converting. I end up with negative, in this case, 270 degrees times pi over 180 degrees. And that negative 270 over 180 will simplify to be a negative 3/2. Again, notice that the degree symbol and the degree symbol will cancel each other out because we have one in the numerator, one in the denominator. Now in this next example, we don't end up with a number that makes a nice fraction. We end up with something that is a decimal. And so in this particular case, you're just going to type this into the calculator and use the pi symbol in the calculator, and it will convert everything for you into this radian measure here. Now, notice that when we have a radian measure, there's no degree symbol listed, right? So no degree symbol. That's how we know when we have a number that it is radians and not degrees. And remember, if you're doing any calculations, to switch your calculator into the radian mode. If I list this number 30, this means 30 radians. If I list this number, this means 6.5 degrees, right? We don't judge the number based on whether it's a large number or a small number. We judge it based on whether or not it has the degree symbol written. Going in the opposite direction when we want to convert from radians to degrees, in this first two examples, they're examples that have a pi symbol given to us. And so it's easy to see that when I write this fraction, I'm going to write it with the pi symbol in the denominator, so that pi in the denominator and pi in the numerator will end up canceling. And multiplying across, we'll have 9 pi times 180 over 4 times pi. The two pi symbols will cancel, we'll multiply here, and we end up with 405 degrees. This is the same idea in the next example. Notice that we have our original radian measurement had pi in the numerator, and we multiply with that pi down in the denominator to get negative 150 degrees. But when we're given a number that doesn't have a degree symbol, we have to think about putting in the numerator what we want to end up with. What we want to end up with is degrees overall. And so if I write this as a fraction, mathematically, we would have 4.25 multiplied by 180 degrees. And I want degrees to be my final answer, so it's in the numerator. And then in the denominator, I have 1 multiplied by pi. You can plug this into the calculator as it is, and it will give you this 253.5. And then you'll add the degree symbol to show that it's degrees. We're mostly going to use the decimal degrees, not so much the degrees minutes version. This sort of reiterates what I was saying before, that if there is not a degree measurement, then we assume that the measurement we're being given is radians. Here are some of the equivalent measures that match up with the common angles that we've been using from our special triangles. Remember that pi is equivalent to 180 degrees. So in this first example, if we take 180 and divide by 6, that'll give us 30. And if we take 180 and we divide it by 4, that'll give us 45, and so on. These numbers that they've listed here is plugging into a calculator pi divided by 3, and you'll get that approximate value of 1.05 radians. There's a copy of the unit circle posted in Canvas that you can use to see these equivalencies. And there are simple calculations that you can do to go from radians to degrees. You're going to be substituting pi for 180, right? Really, you're multiplying by 180 by pi, but what ends up happening is that 180 ends up in the numerator, sort of in the place of pi. And then in the other direction, to go from, let's say, 150 to radians, you'll multiply by pi over 180 degrees. That, right? This slide has examples of coming up with the trig values for angles that are given in radian measure. So for this first example, we're finding the tangent of 2 pi over 3. What they've done here is transfer 2 pi over 3 into degree mode. But eventually what we'll want to do is actually just memorize where this is on the unit circle. And then knowing what the sine and the cosine are, we'll use that to find the trig value of negative square root of 3. Similarly here, they're taking the sine of 3 pi over 2. Well, where is 3 pi over 2? 3 pi over 2, if this is pi over here, we said, and this is 0, and this is going to be pi over 2, right? Cutting that distance in half. Well, 3 pi over 2 is going to be down here. So it's asking us what's the y value when we're at, in this case, 270 degrees. Well, out here on the circle, the y value is going to be negative 1. Right, this distance here is negative 1 because we're considering now that the radius of this is going to be equal to 1. That matches up with what we're getting here, and we can figure that out without using a calculator. The last one is giving us a negative angle, but similarly, we are taking, in this case, the cosine of negative 4 pi over 3. There's a theorem we haven't talked about yet, which is saying that if I'm looking at cosine of a negative angle, I can take the negative sign out into the front. But most of you guys are going to be using calculators for these, so don't stress too much about that theorem at this point. Just know how to get these answers in your calculator, and make sure when you're doing this calculation, if you're plugging this one in, make sure that you have your calculator in radian mode, otherwise you'll get the wrong answer. The next section has a couple of application problems, and they're related to the arc length of on a circle, and then also a sector, which is sort of like a piece of pie. So here is a formula that we'll be using. We're using the letter S to represent the length of an arc. It's going to be this distance on the outside of a circle. The central angle just means the angle that is sitting next to the origin. So this angle here in this case, or this angle here in this case, right? And then the radius, of course, is the distance from the center of the circle to the outside of the circle. So the radius would be this length or this length. We've got a lot of radii here, right? A lot of different options there. So the arc length is going to be the radius multiplied by the central angle. But one of the things you need to notice is that for these formulas, when we have application problems, the angle measurement has to be in radians. So here's an example. We have a circle and the radius is 18.20 centimeters. We want to find the length of the arc right here on the outside of the circle. And they've given us the measure of the central angle at 3 pi over 8. Now the last slide told us that this is the formula that we'll use. The arc length is the radius multiplied by the central angle. We'll plug the radius in here. Here is our angle. And just plug that into a calculator to get our answer here. Pretty easy. This next example, though, is one in which we're given an angle measurement in degrees rather than in radians. So to use that formula, we have to first convert 144 degrees into radians. So you can see that part right here. They took 144 degrees over 1, multiplied it by pi over 180 degrees. And in the calculator, this will give you 4 pi over 5. Now, if you're using Desmos, a little tip is to not plug in the pi symbol. So here's a tip for Desmos. In the calculator, you'll type in 144 over 180. And then when you hit enter, it'll probably give you a decimal number, but there's a little fraction button on the left-hand side that you can hit. And what it'll do is it'll give you the answer of 4/5 so that you have a nice fractional value. And the pi symbol, obviously, of course, is going to go up here. So we just kind of ignore the pi symbol if we're going to use Desmos to simplify the fraction for us. Because if we type in pi, I think sometimes what it'll do is switch it into decimal for us, and it might not be able to get it back with the pi symbol for us. So now that we've converted the angle from degrees to radians, we can plug it into our formula. We've got the radius here, we've got the angle here, and then this gives us the arc length. Here's an application problem we can use to find the distance between two cities. The latitude, you guys have probably heard of latitude and longitude, right? Latitude gives the measure of the central angle with the vertex at the Earth's center. So we've got the center of the Earth here. And so if we think about the equator, and then we're measuring up this way, latitude, think of latitude like a ladder. It's measuring like this, right? It's telling us that the latitude of Los Angeles is approximately 34 degrees north, and for Reno, Nevada, it's about 40 degrees north. And so what we're trying to do is find the distance between these two cities, or the arc length here, right? Because the Earth is curved. So just by looking at this picture, we can see that the central angle between them is going to be 6 degrees. And so in this first step, what they've done is they've taken the 6 degrees and converted it into radians, pi over 30 radians. Now we need to know the radius of the Earth, right? Because our formula calls for the radius and the central angle. So that first part we did was to find the central angle. And they told us that the radius of the Earth was about 6,400 kilometers. So plugging in the radius here, and then here's the central angle, plugging that into a calculator, we get that they're about 670 kilometers apart. So let's see, how many miles is that? So let's change this into miles because that makes more sense to us. We know that 1 kilometer is about 0.6 miles. I know that because if you've ever run or raced in a bike race, a 10K is about 6 miles, approximately. So if we take this number of kilometers and we multiply it by 0.6, see, we've got 670 kilometers. And similar to what we were doing before, I'm going to multiply this by miles and kilometers. I want the kilometers to cancel, so I put it in the bottom, 0.6 miles in the top. So I'm ending up multiplying 670 times 0.6, and I'm getting about 402 miles. That's probably as the crow flies, right? Not if we were actually driving. All right, here's a second example of a piece of rope that's wound around a drum. You can kind of see the rope. It's a little bit hidden in this picture. It's going here on the outside. And if the drum is turned, it's just like a big, huge cylinder. If it's turned 39.72 degrees and the radius is 0.8725 feet, how much rope is going to be wound around the drum as it rotates? So again, just using our formula, arc length is radius times central angle. They have the radius listed here. This measurement is in degrees, so they're converting it to radians, all in the same calculation. Plug that into your calculator and you'll get this length of rope that's wound around. Okay, that is all that I have. Thanks for watching, and I'll see you in class. Have a good day.